me on Monday.
We want to hear
You
your
can
voice.
listen to yourself on Monday.
Oh, God.
That's even worse.
You can listen to the voices in your head.
Yeah, you don't want to hear my
Why would you
thoughts.
do that? If you stop talking, the voices get loud.
Right, the voices get
We
louder.
listen to music like in headphones.
You may listen to music with your headphones. I'm fine with that. With the understanding that I can come by and listen.
What if it's Nickelback?
If that's fine.
Okay.
As long as it's not so loud that it's, you know, that if I can hear it, then I'm going to come ask you to turn it down. But I'm fine if you have it. You have to be listening to music, though. You can't be listening to math lectures.
Why not?
You can listen to Taylor Swift. Yes. You can listen to Taylor Swift. T-Swizzle.
Swifty.
You can. What is that stuff? One of my sons listens to all the time. What's that? EDM, RDM, MDM. No.
What?
What is it? EDM?
Yeah, it's EDM.
Electronic. EDM. That's all my kid listens to now. Let's hear the shaking.
The speakers are smoking.
Speakers are smoking. It's not all that's smoking right now.
Colorado.
I know.
Boulder jokes.
Yeah. Yeah. Okay, so let's first talk about some of the parameters. There'll be about 15 questions, no graphing calculators, and this is the one that's going to really irk some of you. No calculators with an integral button, because this one has an integral button, and it's just not fair unless everybody's calculator has an integral button.
Then let's go to the one on that one.
So if Logan wants to purchase this calculator for everyone,
What's the calculator called?
this one is a TI-36X Pro, which is kind of the most convenient calculator these days that's non-graphing. But the problem is it does do integration, so you can't use this one.
This one?
That one's fine. Oh wait, does that one have an integral button? Oh, that's a Casio one, yeah.
How many people are
I
in the
know,
class?
I know. Most people don't even know how to use it. How many people what?
How many people in the class?
Take off.
Like 30? Wait, what are you doing? Is your family rich?
My dad works for Amazon, so we get a huge discount.
Oh! There we go. There we go. That's right. Okay, so no note card, so you need to know your formulas for this test. You get a note card on the final where you have everything matched together. But in Calc 2, these chapter exams, the formula is the concept.
What?
Like plugging numbers into the formula is not the concept. The concept of understanding surface area, that it's 2 pi r ds, that's the concept. If you're not, plugging things into a formula is not math. That is not math. That's what, cooking or something?
Yeah,
Where
that's
you-
baking.
Baking. It's baking. Right. So yeah. So you need to know your formulas for a chapter exam. My job is to prepare you to go to CU, CSU, and Colorado School of Mines. So you will.
Wait, what did you say?
Nothing. Okay, so let's go ahead. We'll go through the practice problems that we have. We'll go through the practice problems that we have up here in the slides. And if you have homework questions that you still haven't gotten, we can go over those during the break or after class for a few minutes if I don't get to something that allows you to figure out what your question is. So we'll start by just doing some stuff from chapter 6. And we won't get through all of these. So all of these, they're all labeled. We're not going to get through all of them, but we'll get through enough of them that you should feel prepared for the test on Monday. TGIM. The best Monday ever.
All right.
Right on. Okay. So let's take a look at this first one. Way back in chapter 6, this probably feels like a long time ago. They ask us to use for both methods when we're trying to find the position function from velocity. There's two methods, the fundamental theorem method and the antiderivative method. I don't care which one you use. I don't care. I will use the FTC method just because I think that's the better method. It's the more conceptual method. It's the method that, going forward is usually used in a lot of classes. So the position in the future, so that's what S of t means. It means the position at a future time. And that begins with the current position. The future position depends on where you start. So that's the first part of it. And then it depends on the displacement that occurs over the time interval. And this integral right here is the integral that gives us displacement. If you integrate the derivative of s, you get displacement. What is the derivative of s?
Velocity.
Velocity. So we just plug all this stuff in. So s of 0 is 3. We're integrating from 0 to t. S prime is v. And we do a quick change of variable here. We change it over to x's because this letter x is representing the integration variable. It's a dummy variable. It's going to go away. But we don't want that variable to get tangled up with the t that we've already used as the independent variable. So that t right there is already used for a different purpose. The t right here is the independent variable for the function that we are finding. So are all of those chairs broken back there?
Sorry.
All messed up? Wow.
Sorry about that.
Is that one okay? All right.
That's just Jack my
No.
Don't listen to him. He's crazy. He's going nuts.
Voices would like to disagree.
The voices would like to disagree. So then we just do our integration from 0 to t. Future position is current position plus displacement. S prime is v. What?
I can't write fast enough.
Don't write it all down. Write every other step. It's like when I was in English, I read every other page. Right?
That's why I'm not teaching.
I got through.
Hey, the worst.
Right?
So in this case, because you're looking for future position, that 0 to 4 is just kind of there to throw you off.
The 0, 4 is there to just sort of, the t value right here, we're imagining it somewhere between 0 and 4.
Okay.
We do not need the 4 unless they say what is the displacement on a given interval. But the 4 is nowhere going to come into play down here.
Okay.
That interval could say 0 to 10 and we'd have the same answer.
Okay.
Yeah.
So that would be used on like part B?
I don't need to see a part B.
Well, if there was a part B.
Yes, if there was a part B, yes. If there was a part B, yes. Then that's funny. It's going to be used in part B. Yeah, I don't know why they put that there.
Does that constrain the usefulness of the position function?
I
Like,
mean-
you can only say it's valid on that interval?
I mean, that's like if you're doing a population model, usually you're going to have some sort of constraint and say this is going to be good for like the next 3 or 4 years. But this population model is not going to be good beyond that. So usually that interval is because based on some sort of reality, they know the model is not going to persist. You know, so there's somehow they've come up with the constraint that that new function is only going to work between 0 and 4. Or something. Or it's 99% accurate between 0 and 4.
So using like the position function to find position at time 5
Yeah.
would be not.
It might not be that accurate.
Okay.
You could still predict, but it might not be as accurate if you go outside that interval.
Okay.
Yeah. So it's usually somehow they are going to constrain it. Any questions on that? Finding position from velocity.
Not yet.
Eliana, questions?
No.
No. Alex?
But then you wouldn't solve anything for that one?
Oh, well, if the question said, what is the predicted population, if they say, what is an estimate for the population at t equals 3, then we would plug in t equals 3. So if there was a part B that said, find the population at time 3 or time 2 or whatever, then we plug it in. Yeah. Roberto?
You would just plug in that 3 hypothetically into just that one right there.
Right
You wouldn't
there.
plug it into the original.
Yep. Right there. Okay, let's do one with a population. So this is just the generalization of that. So, and this sort of is like the question you just asked, Alex. It says, what's the population after 14 days? So the future population is going to be the initial population, and 0, plus the change in population. And the change in population is the integral of its rate of change. And we will put an x in here instead of a t. So that is the fundamental theorem of calculus method. That's our general concept, that the future value of n will be the initial value of n plus the change in n. And the change in n is the integral of the derivative. That's going to give us the amount of change. If you integrate the rate at which something changes, you're going to get the change in that variable. So they tell us that we're going to start with 200 cells of some bacteria. And then we're going to integrate the rate of change. So we'll integrate 0 to t. And the derivative that they give us, 50e to the decimal. So that's it. That's the basic setup. We want to integrate the rate of the rate of change for the population. That's it. Now we're integrating an exponential. What's the integral of an exponential? Itself divided by
the derivative of the top.
derivative of the exponent. Yep. So that is 100%. So first we're going to get itself, and then we divide by the derivative of the exponent. So this is called the reverse chain rule. And then this will be evaluated on the interval 0 to t. Great. So here's one common place to make a mistake. When you're evaluating this antiderivative at t, no problem. You just turn the x into a t. But when you evaluate at 0, it's very tempting because many times when we evaluate at 0, we get 0, but we do not get 0 here. So beware. Don't make that faux pas. And when we plug in 0, what is e to the 0? 1. Yeah. So that is our final answer. We can combine our constants if we want. We could combine these two constants. On a test, you would want to combine them, but our focus is going to be on the setup. So one thing, we know that the initial population is 200. So this model, if we plug in t equals 0, better give us 200. Does it? If we plug in t equals 0, do we get 200?
Yeah.
Yes. Because when t is 0 right here, then this e to the 0 becomes 1, and we get 50 over the decimal minus 50 over the decimal. They cancel out, and we're left with 200. So that does match our initial population.
When we do the exam, do you want us to solve it, or do you want it to end right there?
You should combine the two constants.
Okay.
And it will tell you like what to round to or whatever. All right, let's move on from population. Area between curves. That's kind of built into a lot of what we're doing with the shells and the washers already. So let's not just do that by itself. You can do that on your own. Let's do a slicing one. This tends to give some headaches. Right, Celeste?
It does.
Does that picture make sense to you?
Yeah.
No? So it's the one thing that I notice tends to throw people really off is that this perpendicular to the base. So you just want to remember that all our cross sections are always perpendicular to the base. So our base is a shape. So the one that we were working on, it was that semicircle. That's our shape. And then the cross sections are always perpendicular, but we need to know, are they perpendicular and parallel to y, parallel to x, perpendicular to y, perpendicular to x. There's 4 ways that this can be given. So they could say parallel to y or perpendicular to x. Those are the same. They could say perpendicular to y or parallel to x. Those are the same. So there's 4 different ways they typically do it. And that one problem with the semicircle, you had your semicircle, and then it said, draw the perpendicular cross sections parallel to the diameter. So that's the same idea. So for that one that we did, which had a base of a semicircle, that means that our element is going to be parallel to the diameter. The cross sections will be coming straight out of the board as squares. So we don't draw a vertical element there because that's perpendicular to the diameter. So that would be important. You just have to pay attention to that. So let's see. So here they tell us that our base, we're going to have a base for our solid that's coming from this triangle where we have these 3 points as vertices in the origin. So that is going to be our base. Now we know the cross sections are coming straight out of the page. Right? They're perpendicular to that base. They have to be. But this is the important thing. They say they're parallel to the y-axis. So that automatically, we don't even care what the shape of these are yet. Automatically, we know we're here. We know that the vertical element is necessary because we're drawing cross sections that are parallel to y. Or they could have said perpendicular to x. Those are the same. Perpendicular to x, parallel to y.
And that means dx.
And that means that we're going to have a dx automatically. If we have a vertical element, the thickness of a vertical element is dx, which means we integrate with respect to x. Horizontal, we have a dy. So now let's talk about the shapes. Oh, the shapes are semicircles. So that means that we're going to have all these semicircles coming straight out of the board. Pretty hard to draw, but you can imagine if the base is my hand, we just have a bunch of semicircles. And it should be pretty obvious that the radius of these semicircles is getting smaller as we move to the right. There's the radius. If we move to the right and we draw a semicircle right there, that semicircle is going to have a smaller radius, right? So it's almost like, you know, it's almost like half of a cone, like a birthday hat type cone. Almost like half of that, except the birthday hat cone is symmetric. This is kind of skewed a little bit. But cross sections are all semicircles. Any issue? Someone call code? Any issues with that picture right there? Do we know what everything represents? So the one big difference here with our cross sections being semicircles, areas of semicircles are found by looking at the radius. The function that we're going to build that represents this diagonal line, that's going to give you this entire distance. That's going to give you a diameter. And if we want the area of a semicircle, we have to divide by 2 to get the radius. All right, so let's find the equation of this line first. What is the equation of that line?
Negative x.
Y-intercept?
Plus 2.
Plus 2. So the slope is -1, but the y-intercept is 2. So negative x plus 2. That'll be the, or you could do point slope with one of the points. Doesn't matter. Okay, so what is the radius then of the semicircle at x? Isn't it? It's just this function divided by 2. Right? Just going to divide that by 2. That'll give us our radius. Multiply that by half. Because that function, negative x plus 2, is finding the diameter of the semicircle. It's measuring the distance from the x-axis all the way up to that diagonal blue line. We only want half of it if we're going to find the area of a semicircle. So the area of the semicircle is 1/2 pi r squared. Area of a circle is pi r squared. Area of a semicircle is 1/2 pi r squared. So for us, 1/2 pi multiplied by the radius squared. So we're going to square this radius. And that will give us the area of our cross-sectional semicircle. Squaring the denominator is a 4, so we're going to end up with 1/8 times pi. And you could write it as pi over 8. That is the area of a semicircle. All right, issues. Spiel them out. No issues? Issue.
Mine is definitely the radius part.
Uh-huh.
So,
This right here.
yeah, so wouldn't you just go straight to the area of a semicircle, 1/2 pi radius squared?
That's what we did.
Oh, and your radius is because the semicircle is half, right? Because the radius is...
Half of the diameter, and the function is giving you the diameter. This function here is measuring all the way across. So then we divided it by 2, and then we're plugging it into what you just said, half pi r squared.
Oh, okay.
Mhm.
So, I'm assuming you took that half out and it became a quarter?
So this 2 will square that and make a
Right.
4th, and a 4th times a half is an 1/8. Right. And so then we are going to integrate this, so we'll just write down the volume equation. We're going to factor out that 1/8 pi. What are the limits?
0 to 2.
0 to 2. And are you getting those limits of integration from the y-axis or the x-axis? X-axis. I mean, here it's a little ambiguous because both are 0 to 2, but it's coming from the x-axis.
Because it's going like this, right?
Yeah, exactly. Yeah. And then you integrate that and you get your volume. Any problem with anything else on there? Problems? Problems?
About the test. Do we get like a note card or anything like that?
Oh yeah,
'Cause
no.
no.
So no.
Well, like no, because someone had asked about like if we get the formulas of the.
Yeah, not on a chapter exam. On the final exam, you get note cards because there's a lot of formulas overall. But for a single chapter, the formulas, what I was saying earlier, the formulas are the concepts. Like knowing the area of the knowing how to, well, this one's not a great example because you know the area of a circle already, but like if you're doing the arc length one or the surface area one, understanding that the integral for surface area is 2 pi r ds, that is the concept, right? The formula and the concept, like just plugging the numbers into the formula, that's really not the concept. Like that's prerequisite stuff. But it's sort of understanding those basic formulas that's important. So you need to know the basic derivatives and integrals of the hyperbolics, and then you need to know the formulas for each of the ones that we're going to do today. Yeah. So if you look, the formulas that we are going to use on this exam, if we come over to handouts and we go here, these are the formulas other than the derivatives of the trig and hyperbolics and integrals. These are the formulas that could show up on the exam right there, those 12. Those are the ones. Which, hopefully, there's not one that you look at and don't know at this point. Dan?
Sometimes I get tripped up by just algebra and geometry and stuff.
That's usually the hard part.
So for geometric formulas that we should know, what shapes should we know the formulas of?
Circles, squares, and triangles.
That's it. No cones, no cylinder.
I mean, the cylinder you would need to know 2 pi r h when you're finding the shell method.
Mm-hmm.
So the shell. So when we think about the geometric shapes that we use disks. So those are pi r squared. We use washers, which are pi r squared minus pi r squared. Outer disk minus inner disk for the area of a washer. And then we use cylinders, 2 pi r h. 2 pi r is circumference around the base and then the height to get the full area. So those are the shapes that we've seen. The other place where we might see a shape is what we just did, where we had cross sections that were semicircles or cross sections that are squares or cross sections that could be triangles possibly. So those are the general geometric formulas: disk, washer, cylinder, square, semicircle.
So for the application stuff, like, I won't need to know how to find a certain side of a parallelogram?
No.
Or, no, okay.
Because remember that with those application ones, so we have those two formulas that we see, the ADD volume and ADD area. What we meant by those was area of a rectangle if we're doing the force problem, the pressure on a wall, the force on a wall. So it's the area of a rectangle, length times base. And when we're doing the other one, the cross-sectional area, well, the volume, ADD volume, we did a cross-sectional area times dy, and those cross-sections were discs or rectangles. Yeah, so nothing more complicated than that. Yeah.
Okay, thank you.
All right, so let's go to a washer problem. We have a disc problem here, but let's make sure we can get something of everything. And a washer is 2 discs in one, so let's do that. Washer problem is 2 discs in one. So the first thing that you want to be able to do is identify whether it's a vertical or horizontal element. And that all depends on the axis you're rotating around and what the shape is. So here, this one doesn't tell you, but on the test I will tell you. And what we want to do here is use washers. I put it up here using washers. So if we want to use washers and we're going around X, should it be vertical or horizontal? I've heard both.
Vertical.
Vertical. So it is vertical because as we rotate, right? If it's parallel, you're going to create a shell. Parallel shell. Parallel shell. Parashell. Perpendicular washer. Doesn't rhyme, but whatever. Perpendicular washer. So if it's not a shell, it's not parallel. All right, so that is going to create a washer. When that little element there rotates around, it's going to create a washer. The area of a washer, so let's write that down in generic form over here. It's pi times, if you want, you could do it like this. If you want to think of it this way, conceptually, it's the big disk minus the little disk. That gives you the area of the washer. You're subtracting off the area of the hole. That's going to give you the area of the washer. So when we come back and look at our picture, when we're trying to identify any radius, if it's the radius for a disk, if it's the radius for a cylinder, if it's the radius for a washer, start at your axis of rotation. And for an inner radius, it's going to be the first function that you hit. That is your inner radius. That is going to be the radius of the hole of the washer. So starting at the axis and going towards your region is a good strategy. Your outer radius, same thing, except you pass the first curve and you're going to go to the outer curve. When you look at your element is trapped between two curves. The inner radius is going to be the closer curve that it's trapped by, and the outer radius is the furthest curve that it's trapped by. So that little blue element is trapped right in between these two curves. Okay. Now we need to figure out how to write the Ri and the Ro. Before we do that, tell me this. Will this volume integral have a dx or a dy? Dx. Because this element is vertical, its thickness is dx, that tells it that this has to be a dx there. Anytime you have a vertical element, you're integrating with respect to x. Anytime you have a horizontal element, you're integrating with respect to y. So that's just a checkpoint. So right there, we know that when we write down Ri and Ro, this is just an extra checkpoint. We know, oh gosh, this can only have x in it. This cannot have y in it, because those have to drop into the integral with a dx. So that's a clue. It's something that we can use to double check that we're using the correct variable. So when we look at our Ri, well, let's go with Ro first since it comes first. So RO, that's a vertical distance. A vertical distance is upper y minus lower y. So we look, there's the upper y, there's the lower y. So RO is the upper y, 32 root x, that's the upper y value, right? That's the y value, minus the lower y value. Oh, I said that wrong though. What is the lower y value? So this whole distance here, right here, this whole distance, not just the length of the element. I started thinking about the length of the element, which is more area than volume. So if we look at RO, what is that full distance?
32.
Isn't it just 32 root x minus 0? Right,
Yeah.
this lower y value is 0. Right, we're going all the way to the axis of rotation. When I just spoke, I stopped right there, but we want to go all the way down to 0. So it's that. That is the outer radius. That is the distance from the axis of rotation to the curve furthest from the axis of rotation. And what would Ri be?
8x.
Just 8x. So then our formula, when we plug it into the area of a washer formula, we're going to do RO squared, so 32 root x quantity squared, minus Ri squared, so minus 8x quantity squared dx. And limits of integration.
0 to whatever.
0 to the intersection point there, right? How do we find the intersection point?
Set of equal.
Set them equal to each other, find the common x. So set them equal to each other. We have 32 root x equals 8x. Let's divide out the 8, clean that up. Anytime you have a square root equation, square both sides. Get rid of the square root. So 16x equals x squared. Nonlinear equation, everything to one side and factor. That is your general strategy for solving a nonlinear. So this tells us that x is 0 or 16. Everything to one side and factor. So our upper limit will be 16. So everything to one side and factor. All right, any questions on that setup? That's the part that's most important. It's the part we're going to focus on today. So that's 32 squared, whatever that is. When we square this, we'll get 64x squared. And you know how to integrate that. Any questions on the inner radius or the outer radius? Yeah?
When it's like that, you could just take out the 64 and the 32, right? And move them to the front, or no?
Once we square the 32, we could pull out the 64 if it's in both of them.
Oh, okay.
Right? It has to be common to both if it's going to come all the way to the front.
Because it's subtracted.
Because there's a subtraction in there. So we have to pull out, if we pull out anything, it has to be common to both sides of the subtraction. All right, let's go to a cylindrical shell. So here we're going to rotate around the y-axis.
What is this again?
Cylindrical shell, volume. So let's think to yourself for a moment. Think. Be honest. Vertical or horizontal element for a shell. Going around the y-axis. Okay, tell me. Vertical or horizontal? Vertical. Shell, parallel.
Yes.
All right. Shell, parallel.
Can we do like horizontal?
If we do a horizontal, we're going to get a disk. So if the element is perpendicular to the axis, this rotates around and creates a disk, not a cylinder. So that is a disk, but this is a cylinder. So they've got to be parallel if you're going to create a cylinder. Perpendicular, it's going to create a disk or a washer. So parallel for a shell. So we want to use shells. Okay. The generic area of a cylinder or a shell, interchangeable word in this context. So the area of a cylinder is the circumference of the base, 2 pi r, circumference of the base, multiplied by the height. So there's one of the geometry formulas we need, 2 pi rh, area of a cylinder. Now, let's just write down quick generic thing. We've already drawn our element. The second we draw our element, we know whether the differential inside the integral is going to be a dx or a dy. And what is it going to be in this case? Dx. It's the thickness of that vertical element, which is dx. So right away we know that. And that's just a nice clue. It's a mental reminder that when we replace the r and the h, we should just end up with x's. No y's in there. So when we look over at our element, we're rotating around the y-axis. This is the generic element at x. And when we rotate around the y-axis, here is going to be the representative cylinder from that representative element that I drew. So there's the cylinder.
What's the radius?
What is the radius of this cylinder? X. That's what x represents. X represents the distance from the y-axis over to that element. That's the radius. What is the height of this cylinder? It's the function. Right? That function in our picture, let's see if we can draw it in our picture. This distance right here is the radius, right there. And this right here is the height. So the height is just the function, which is 8 divided by 1 plus 8 x squared.
Mr. Lewis,
Yes, question.
can you just put an x right next to the 8 outside the parentheses?
X right next to the a x parentheses where?
Can you just change the function a little bit, make it easier?
This?
to roll? Yeah.
How are we going to change the function?
Can you just make it easier?
And do what?
Add an x in the numerator?
Yeah, that's what we're going to do. When we multiply?
Yeah.
Yes. So now we're going to have 2 pi rh. So we're going to put the x in the numerator. So we're going to have this. Like that. Okay. What about limits of integration?
0 to the function.
0, you said it, 0 to. Roberto?
So one of my questions is, what happens if we have two functions instead of just one?
You do have two functions.
Yes.
X equals 0.
Okay, but not x equals 0. Something else.
Then you would have to use whatever that other function is.
Okay, so you would multiply. Oh no, you would subtract.
You would subtract, yeah, you do, you know, whatever the letters are, P minus Q, F minus G. Yeah.
Okay. And that would be your height, right?
So this right here is the height, so it's going to be the upper function minus the lower function. Your radius would be the right function minus the left function. So with the shell method, you always have both directions happening simultaneously. That's why it's harder. Okay, what form is this integral?
Write that down. Natural log.
So does everybody see that? So that integral is in log form. Oh, curious. So let's rewrite this a little bit. I'm going to multiply the 2 by the 8 and put that in the numerator. And that integral is in log form. The derivative of the bottom is 16x. Well, that's in the numerator. So that means it's in log form, which means we can cut to the chase. So this is log form. And we know that anything in log form integrates to the natural log of the absolute value of the denominator. If you didn't notice that it was in log form, you would use u substitution. And what would you let u be?
1 plus 8x squared.
1 plus 8x squared. And then you'd end up with du over u, natural log of absolute u, and you get the same exact answer. So let's plug in the 2. Plugging in the 2, 2 squared is 4, so we get natural log of 33, minus, plugging in 0,
0.
natural log of 1, which is 0. So we end up with pi times the natural log of 33. That'll be our final answer.
That shell parallel actually helps a lot.
Shell parallel helps?
Yeah.
Oh, good.
Thank you.
No, that's,
I have a question. For the exams, do you care if we use the u substitution or the log form?
no.
Do you have a preference of what
Nope.
we use?
Well, I would prefer you use log form just because it's cleaner. But if you want to use u sub, of course, totally fine.
Okay.
Yeah, totally fine. Yeah.
For shells, do we always use 2 pi RH?
Yes,
Right?
because that's the area of a cylinder. And when we say shell, that's what we mean, cylindrical shell. So shell and cylinder, we're talking, those mean the same thing.
I feel more comfortable with this now.
Yeah, good.
The shell parallel.
Shell parallel, good.
That is
I mean,
so
sometimes you just need a little trick to remember something.
Yeah.
Yeah.
So then the function pi r squared is that when we would do a disk that's touching the
Touching the
axis that we're
axis.
okay.
So the pi r squared, if we have our axis here and it's touching, then we're going to get a cross section that's a disk, so we'll use pi r squared. That's right. You are correct. Let's do a random axis. Why not? Okay, random axis. So these are shapes that you should be able to draw. I'm not going to ask you to draw anything wild and crazy. This y equals x squared. Okay, you know how to draw that. X equals 1, you know how to draw that. Y equals 0, you know how to draw that. There's our shape. Now, this is being rotated around. X equals -7. So our axis of rotation is way over here. X equals -7. Okay, and we're using a shell. So should we draw a vertical element or a vertical or horizontal element?
Vertical.
Vertical. Yeah, parallel for shell. Makes so much sense, right? Parallel shell. All right. The area of a shell, the area of a cylinder, those are equivalent in this context. So the area of a cylinder, 2 pi RH. So now we look at our picture and we have to identify the radius and we have to identify the height. The radius, anytime we have to find a radius, we start at our axis of rotation. So start over here, axis of rotation. Our radius, we just start going, and we stop at our element. That is the radius of the cylinder that's going to be formed by that vertical element. That vertical element rotates around, and the distance to the axis of rotation, that is the radius. So that is the radius.
Plus x.
Say it again.
7 plus x.
7 plus x. So if we think geometrically, this distance right here is 7. This distance right here is x. So that tells us that the full radius is going to be x plus 7. Or you could say you're finding a horizontal distance, so you could do the right x minus the left x. The right x is just x. The left x is -7, so x minus -7 is x plus 7. Whatever floats your boat. Does not matter. So the radius is going to be x plus 7.
The height is just a function.
And the height is just the function. The height is right here. That's just measuring that distance right there. It's the height of the element, the length, the height of the element. So that is the function, which is x squared. How about limits of integration?
0.
0 to 1?
Yeah.
So the limits of integration, remember, are always around your physical region that you're rotating. It has nothing to, bless you, I think, nothing about the gap in between. So these limits are always based on the region itself. Doesn't matter how big this gap is. We're creating cylinders for all of these x's between 0 and 1. So 0 and 1 is where the collection of cylinders is coming from. And then we're going to distribute the x squared. And we have a dx because we have a vertical element. So that will be our volume. Let's set up the same exact one, but with a washer. Same exact region. Let's just set it up with a washer. So let's redraw it so that we don't get too messy in there. So we've got that. We've got our axis of rotation. So first off, horizontal or vertical element? Horizontal. Horizontal element, right there. So this is going to be the horizontal element at a random y. That's going to rotate around and create a washer.
Wait, when they both rotate, wouldn't they create the same shape though? It's just like different ways of.
This is the
figuring
only
out.
thing rotating, this one.
And then the other one.
So the other one, this is parallel. So here we're creating a cylinder, right? These are parallel. If you're parallel to your element, you're going to create a cylinder. This is perpendicular, so you're creating a washer. Right? This rotates around and creates a washer.
But wouldn't they be like the same shape?
Nope.
They're not.
The solid object,
Yeah,
the solid will be the same.
Yeah, that's what I was.
Oh, yeah.
Yeah.
The solid will be the same.
Oh, okay.
But the cross-sectional area will be totally
Oh,
different.
yeah. I get that.
Yeah, you're right. The solid object will be identical.
Okay.
Yes, that's right. That's right. Okay, so the area of a washer we know is going to be pi times the outer radius squared minus the inner radius squared. So now we have to look at our picture and decide where our I and our O are. So again, any radius, start from your axis and just start moving towards your region. That is a very good strategy. Anytime you have an R, start at the axis and just start trucking across. The first curve you hit, that is the inner radius. That is the left-hand curve bounding the element. And our O, start at our axis, start trucking across, and the second part of our region will be our O.
That's just 8.
So, with our volume formula, what is going to be the differential, a dx or a dy? dy. Anytime we have a horizontal element, has to be dy. Anytime we have a vertical element, has to be dx. So that just gives us a little bit of comfort. That tells us, oh, we know that when we replace the RO and the RI, we only can have y's. There can't be any x's in there. So we know that we should have a bunch of y's in there, pile of y's. Pile of y's. Y. So RO is 8. So this x value right there is 1. So RO, horizontal distance, right x coordinate minus left x coordinate.
Sorry, what did you change about this graph versus the last one? Are we just taking this one in terms of y just because, or?
Just because, yeah.
Okay.
So this one we wanted to do it with cylindrical shells. This one we're going to do it with washers. But it's the same solid object. Same solid object. So we'll get the same volume.
So are we going to have like, are we going to be expected to determine whether we should use this one?
No.
Okay.
I'll tell you.
Okay.
I don't want you... You could go down a rabbit hole very easily So I'll tell you, use the shell method, use the washer method, use the disk method, yeah. Yeah, I don't want you to blow a gasket trying to figure out which method's best. So RO, horizontal distance, we do right x minus left x, so that's 1 minus minus 7, which is 8. Or you look at it and you can say geometrically that's 7 from there to there, that's 1 from there to there, total is 8. Whichever method, whatever makes the most sense to you. How about RI? That's going to be the harder one.
Is it x squared plus 7 or not?
Positive root y?
So when we look here, we
Oh,
know
yeah.
that we need y's. So first off, we're finding a horizontal distance. Horizontal distances are x differences. So we take the right x minus the left x. So we have to come in here and say, oh wait, what is this right x? Well, it's been presented, it's been given to us as something that's measuring height, right? Y equals x squared is measuring this way. So we change it, we take the square root of both sides. So it's going to be, Dan, what did you say?
I said positive root y, but I guess do we also have to add 7 to that?
Minus 7, so that's going to add 7, yes. So when we write it as positive root y, we are now measuring this direction. We're measuring that distance right there. That x value is measuring across there. And then we have to add 7 to it. So it's going to be root y plus 7. So this will be minus root y.
Minus 7. If you distribute
did
or
we?
no?
Our outer, so root y minus minus 7, so plus 7.
Square. Oh.
So it's RI quantity squared. So the distance RI is this x minus that x, so it's root y minus minus 7, and then we have to square it. So let's write the guts of, and what about limits of integration?
0 to 1.
0 to 1, and these are coming from which axis?
Y.
Y-axis, good. So it's going to be pi multiplied by 64. All right, foiling. Square root of y times square root of y is y. So we're going to minus y.
Plus 14
Plus 14 was
root.
And then we have to distribute the minus there, right? So that's going to be 14 root y, so it's going to be minus 14 root y. And then plus 49, but we distribute the minus, so we get minus 49. And that will give us the same answer. If we worked out both those integrals, we'd get the same answer. So both of these are the same answer. All right, any questions on setting up that washer method? So washer method, washer method, shell method. If you understand both those, that's great. If you don't understand both those, sorry. You're in trouble.
springs.
You still have some time to figure it out, right? Yeah, you guys are lucky. You get the whole weekend to just like hammer math.
You think we're gonna do
Wow, I'm so lucky. So lucky. So strategic. Taking the class on Monday, Wednesday.
Wow.
Right? Okay, let's do an arc length one. So let's make sure we understand that arc length, that's S, that's the integral of ds. Right? S is measuring distance along a curve. ds is the little tiny change along the curve. It's a differential along the curve. Again, we've said this a few times, we don't know anything about S. Everything here is in terms of x. So that's worthless to us. So we have to convert it. So this gets converted using a Pythagorean theorem. If you go back and look at our notes, there is our arc length formula. So all we did was use the Pythagorean theorem there. All right, so the function that we're given, we have to take its derivative, square it, add 1, and throw it into that square root. You can imagine if you just pick a random function and you differentiate it and you square it and you add 1 and you put it in a square root, most likely that is not going to be integrable. So these functions that we're finding arc length for have to be nicely sautéed so that we can end up with a reasonable integrand that we can integrate. If you just pick a random function, it's not going to be, most likely it's not going to be integrable. Because you're taking the square root of something. And there's nothing on the outside of the square root. Most of the square roots you've seen integrable, there's something on the outside. So that gives you a u sub thing. Okay, so let's find our derivative. 4/3 times 3/4 is 1. And then we subtract 1 from 4/3 and we get 1/3.
Does that say y to the 12th in the radical?
Right here?
Yeah.
No.
Oh.
What does it say?
Y prime squared.
Y prime squared. Yeah, not y to the 12th. Let me rewrite that as a slightly more sideways tick. There we go. That's better. Yeah. Yeah. If I was asking you to integrate the square root of 1 plus y to the 12th, oh boy, that'd be hard. So the derivative squared. So we're going to take our derivative of the second term here. So that's going to give us 6/24, which is minus 1/4. And then we subtract 1 from 2/3, giving minus 1/3. Okay, so there's y prime. And let me put that perfect square trinomial business over here on the side. So right here is our a minus b. That is a minus b. And we are going to have some stuff going on when we square it. And so remember that perfect square trinomial would be a squared minus 2ab plus b squared. And then we know that if we did a little bit of manipulation and ended up with a perfect square trinomial that only changed the sign of the middle term, we know how to factor that. That's going to be a plus b squared. Okay, so here, this is going to be our a, this is going to be our b. The b does not include the minus sign. So here we go, square. So we're going to square both is square everything here. So y prime squared. So this is where we want to be patient. We want to investigate the middle term. We know that if the middle term is minus 1/2, that's our special case for the tricky trinomial thing. So we square the first term, but not simplify it, just leave it as it is. And then it's minus 2 times a times b. So minus 2 times x to the 1/3 times 1/4 x to the minus 1/3 plus b squared. And again over here, don't simplify, just leave it as b squared. Leave it alone. Be patient. What does the middle term become?
1/2. Negative.
Negative 1/2. So when you look at that middle term, does everybody see that it simplifies to negative 1/2? Mm-hmm. Right, the x to the 1/3 times x to the minus 1/3, that's x to the 0. X to the 0 is 1. 2 divided by 4 is 1/2. So now in our formula, we've taken y prime, we've now squared it. Now we have to add 1. And so here's where we have that trinomial business going on. When we do y prime squared plus 1, the only thing that's changing is the sign of the middle term. And if the only thing that's changing is the sign of the middle term, we just went from this perfect square trinomial to this perfect square trinomial. Right? The only difference is the sign of the middle term. That is the only difference. So that means this is factorable. This one factors into a plus b quantity squared. So that will be perfect square trinomial. It factors into that. And that's very convenient. So our arc length is the integral. They gave us integral limits for x, 1 to 27. Square root of y prime squared plus 1. So we have the square root of a square. Square root of a square. They undo each other.
Oh, that's what I was gonna say.
Where's the plus one?
So when we add the 1 to the negative half, it becomes positive half. This is a perfect square trinomial that factors into a plus b squared.
So
Yep.
before you integrate, you cancel out the squares.
Exactly. Cancel out the square root of the square. So this will be the integral of two easily integrable functions with power rule. So with both of those, we can add 1 and divide by the new exponent. So with the first one, if we add 1 to the exponent, we get x to the 4/3. Dividing by 4/3. Same thing over here, add 1 to the exponent. And if we add 1 to the exponent, we're going to get x to the 2/3. Dividing by 2/3 means multiplying by 3/2. So that's going to give us 3 divided by 8. And that's a plus. Now we're going to plug in the 27. Luckily, we have perfect cubes for both limits of integration. 27 is a perfect cube. So plugging in 27, cubed root of 27 is 3. 3 to the 4th, that's 81. So we're going to have 3/4 times 81 plus 3/8. Plugging in 27 there, we get 3 squared, which is 9. And then we subtract off the antiderivative evaluated at 1. Look at those constants.
And so on the exam, you previously mentioned there would be some indication that there will be a sneaky perfect square triangle.
Right, yeah, so I would just tell you up here, I'd give you a hint. I would say this is a perfect square triangle.
Okay, so we don't have to get down.
You don't have to
see
identify
the
it.
-1/2
So,
first.
yeah,
Okay.
this is how you'd mathematically identify it if you weren't given a heads up, but I will give you a heads up just because it's helpful.
Can you
Thank
go
you.
down?
Yeah.
At the end, wouldn't it be minus
3/8?
3/8?
Yeah, let's see. Ooh, let's see, we're plugging in 1 right here. Yeah, how did I get 3/4?
Well, for the first one, but then plus 3/8.
Wait, let me
wouldn't
think
that-
about that for a minute. 1. Oh, yeah, that's right. That should be 3/8. Yeah, that should be 3/8. Thank you. Yeah, plugging in 1, we get 3/4 and 3/8. Thank you. Phew. Phew. All right, you ready for a break?
Yeah.
Yeah.
So if you told us it was perfect square, could we just jump from?
No! So notice again that this other check in your mind, if you look at the original function there, and you look at our antiderivative there, they match except for sign. That's your check. That is not your strategy.
No, I was just saying, could we jump from y prime to the y squared?
Jump from the y prime to the y squared.
So essentially just jump from y prime
Here
to the blue.
to here?
Yes, just add a square. If you tell us.
Mm,
Or
You need to do something in there.
Okay.
Do something. Not just jump. Don't just jump. Don't just jump. All right, pause. The dot. All right. Surface area. Let's do surface area. So surface area. We need to know our basic surface area formula. And when you're thinking about the surface area formula,
Can I try it?
yeah.
Is it 2 pi the function square root 1 plus the derivative of the squared?
Yep.
The
Yeah.
derivative of the function squared.
Yeah, exactly.
Okay.
Yeah, so usually so if we write it in generic form, we'll do 2 pi r ds, and the ds is exactly what you just said. It's the same thing we had a minute ago. It's the square root of 1 plus y prime squared. So, and r is almost always the function. And this is going to be the square root of 1 plus y prime squared. Yeah, good. So the concept there is that if we have a curve, well, we can draw this one. This one's very easy to draw. So we've got this curve y equals 3x, which is just a steep line. And we won't get too creative here. Let's just say that that's 3. We'll say that that's 7. So we go up to the curve. That's not good enough. So 3 to 7. So that is the piece of that line that we're going to rotate around the x-axis. So the concept is that if you take a point on this segment right here and you rotate it around, that point is going to create a circle. Can I draw that circle better? It's going to be behind, it's going to come out, something like that. Now it's going to take that whole thing and disappear. Okay. Okay, so that point, when it rotates around, that's what the 2 pi r is. The 2 pi r is the circumference of the circle when you rotate a single point. So a single point on there is going to rotate around and create a 2 pi r. And then the ds is the diagonal slant height. So that's what this ds is. This whole thing inside this integrand is a frustum. So that's just a tiny frustum. It's a circumference with a tiny thickness. And instead of the thickness being a dx direction or a dy direction, it's diagonal. And so it creates the little tiny cone thing, the base of a cone. And the integral adds them all together. So 2 pi r, when we look over here, r, again, you go from the axis of rotation up to your representative point, and that distance, like you mentioned, Alex, is the function. That's what 3x does. So that's 3x. That's your r. And then ds is the square root of, this function is pretty easy to differentiate. Y prime is just 3. And then we have to square it and add 1. So we're going to have 1 plus 9 dx. All right, any questions on that setup? So 2 pi r dx. So it's just the only difference between this and arc length is you put a 2 pi r in front, and that r is the radius of the circle that's formed when you rotate a single point from your curve. That's the r. And now what about limits of integration? They give us 3 to 7, so no work there. They're given. So this will be 6. Square root of 10 is a constant. Pi is a constant. So the only thing left is x. From 3 to 7.
Can we have something like this on the test, please?
You like that one?
No, I just like the simplicity.
Yeah, that's pretty simple.
Yeah.
Seems too simple.
No.
No.
Not too simple.
No.
Just enough. So integrate, plug in your 7, plug in your 3, take the difference, la-di-la. Any step there you're not comfortable with? So it's just a little bit more complicated than the arc length, but it's not too bad. A lot of times the surface area ones are a little easier to integrate than the arc length ones, because sometimes that puts something in front of a square root, which makes it a little bit easier. So let's take a look at one more that's a little more complicated. So one of the basic rules we talked about was that if you're finding surface area when you're rotating around x, you want to integrate with respect to x. And if you're finding surface area around y, you want to integrate with respect to y. And this one is commingled. This one says, let's go around the y-axis, but they didn't give us a function that's presented as an x value, measuring from the y-axis. So here we're going to have to do some conversion. So if we're going to go around the y-axis, we want this to have x isolated. That's what we want. We want to write that as an x value. If we're going around the y-axis, we want to be measuring horizontally from the y-axis. So we're going to make that an x value instead of a y value. So we're going to cube both sides and then divide by 3. So we're going to get 1/3 y cubed. So now our function is written as an x value, and we're rotating around the y-axis. That's perfect. That's what we want. The other issue is that this limit, these x values for the interval on the x-axis, we now need to convert them. We need y limits of integration. So how do we get our y limits of integration? We plug our x limits into the function and solve. So if we plug in 0 for x, we get 0 cubed root of 0 is 0. So the y limits will be 0, 2. Plug 8/3 in there. The 3's cancel. The cubed root of 8 is 2. So that'll be our other limit. Now we're good to go. So we have to find the derivative of our function, square it and add 1. There's the derivative. And we can square it and add 1 pretty easily. That's going to be y to the 4th plus 1. So our surface area formula, 2 pi r times ds. 2 pi can come to the front.
X prime, where did you get the y squared?
By taking the derivative of x.
Ah.
So derivative of x right here. There's your function, and that's its derivative. The 3's cancel. Okay, what is the r value then? Say again? Yes. So the r value is the function, just like it was in the last one. So it's the function. That measures the distance to the axis of rotation. And then we do our ds, which is 1 plus x prime squared. That's y to the 4th plus 1. So then our limits of integration we found to be 0 to 2. In the homework, I can't remember if we talked about this or not. Did we talk about the weird way that the help me solve this and view an example do this problem as surface area? Can't remember if we talked about this or not.
I think we did.
Yeah, I think you mentioned it and told us not to do the weird thing.
Yeah, and what they are doing is legitimate. When we look inside this square root, if we're going to use u substitution, which is the natural choice here, we see that the derivative is 4y cubed. dy. Now the one in the homework was much more complicated, and the derivative was really, some weird fraction times y cubed. And what they tried to do was manipulate the front of this so that it matched. And sometimes that's super easy. In this case, it would be pretty easy. We could pull out the 1/3, we could multiply and divide by 4, and we'd get to it. But if it's not totally easy, just do the u substitution and the fractions will work themselves out. There's no need to get hyper creative when you don't need to be. So here we have 2 pi over 3. I'm going to leave a little bit of a space there. And then in here, so we factored out the constants. We have the square root of u. And if we factored out the constant, the only thing that's left is y cubed times dy. So what we're going to do up here is divide du by 4. And that will be y cubed dy. And that takes care of the constants.
So then would that add the times in front of the 2 over 3 times 1/4 or no?
Yes. Yes, exactly. So when we replace y cubed dy, it's going to be du over 4. And the over 4 is a constant. You could leave it inside for now if you wanted, but you can just as easily pull it right to the front as a 1/4. And now we did a conversion from y to u. We have to convert our limits also.
So 1 to 17.
Mm-hmm. So if we plug in 0 up here, we get 1. So that's our lower limit. Plug in 0. Plug in 2. 2 to the 4th is 16. 16 plus 1. Yeah. Those will be the limits. So this will give us pi divided by 6 multiplied by u to the 3/2, adding 1, divide by 3/2, and that will go from 1 to 17. So we end up with pi over 9, 17 to the 3/2 minus 1 to the 3/2. 1 to the 3/2 is 1. So we're going to write this as 17 root 17 minus 1. 17 to the 3/2 is the square root of 17 multiplied by itself 3 times, which is that.
Where did you put the bounds in to get the u sub limits
Mhm.
again?
So we look to our let statement, our u sub statement. So right here, this connects u and y. So when y is 0, plug in 0 and we get u is going to be 1. When y is 2, plug that in and we get 17. So the u sub statement allows us to go back and forth.
Where'd you get the pi over 9?
I thought I just multiplied these. So 2 goes into there once, 2 goes into there 3 times. So multiplying those coefficients. Other pieces?
On the, what's it called? Where you did the u sub,
Mm-hmm.
could you just move that 1/3 out front and then solve
So that's what I did. That 1/3 came right out here. So the 1/3 came out. And we had y cubed dy.
Oh, and then you found.
So y cubed dy is du divided by 4. Yep. So that's exactly right. Yep. Exactly right.
So on the homework for the applications,
Mhm.
there was like this one, I don't think it's gonna be on the test, but you know how like to find k, our constant, it's the force with times a k and then
Yep.
the
F equals kx.
yeah, the x, whatever they give it. But there was one where they give us joules instead of force.
Yes.
And I don't know, I was at the math center and like they couldn't help me either. So it was like really
So let's just look. I don't have one in here that does that, but let's go back up here because we did one in class like that. So let's go to the spring. So I think it was on the second So it's on the next slide. It's here. So with this one, so it says, so normally they give us x and they give us f, and we can find k pretty easily, and that's what this first one does. They give us f, they give us x, so we go f, x, solve for k. The second one here, though, gives us work and distance. So the way we're going to do that is we know that work is the integral of kx dx. So work is integral of kx dx. So they tell us the work is 2. They tell us the distance that we're displacing is 0.1. And so the only unknown here is k. When we integrate the x, it's gone. Right? The limits of integration take away the x. So k is the only thing that's going to be left. So we integrate with respect to x. We get x squared over 2. Limits. When we plug in the limits for the x right here, multiply both sides by 2. Plugging in 1/10 gives 1/100th, and then we get our k that way. So that is another way to give you a way to find k. If they give you work and distance instead of force and distance.
Yeah, I got it.
Make sense?
Yeah.
Yeah. Yeah, pretty interesting. It's a clever strategy. Let's do a spring. There's a spring. So this one gives us another slight twist that I wouldn't give you this slight twist, but I want to make sure you understand it. So normally they give us force and distance or work and distance, but here they give us mass and distance. And so what we need to do is convert the mass to force. And force is just equal to m times a. We know that force is mass times acceleration. And so that's what they're telling us in the parentheses here. So a mass of 700 will have a force of 700 g, where g is acceleration. So slight twist to finding k. But same idea. We just have to keep in mind that mass multiplied by 9.8 gives us force. Oops, mass times acceleration is force. That means, so they give us, and we also want to convert that 2 centimeters over, right? So our force is going to be 700 kgs multiplied by the gravitational constant, 9.8. So there's force. And that's going to be equal to k times x. So we're going to do Hooke's law, which is kx. We don't know k. We're trying to find it. 2 centimeters is how many meters?
0.02.
0.02. So that'll be our k value. Whatever that all gives us. 700 times 9.8 divided by 0.02. So I'm coming up with 343,000. So slight twist, but same idea. They give us force indirectly, and they give us distance. So now we know that our spring has this equation for its force. And that's a very large spring constant. That means the spring is really hard to compress or stretch, which we would expect because we're talking about a heavy-duty shock, so it's got to have a lot of force to compress it. So there's our force function, and now we can answer the question. So again, every spring has its own spring constant. For this spring, that's its spring constant. So it says how much work is required to compress it 4 centimeters. So if we're going to compress it 4 centimeters, we're going to go from 0 to 0.04. Or if we're if we wanted to match reality, negative. It's not going to matter though because we're going to square this and it's going to end. Doesn't matter. Whether you compress or stretch, it takes the same amount of work. So that's the integral we need to evaluate. And when we evaluate this, we get 343,000 divided by 2, x squared from 0 to negative 0.04. And so it's right there that you can see, oh yeah, it doesn't matter if we plug in negative 0.04 or positive 0.04, it's going to be the same work. So plug that in and we'll get what we get. So it's going to be 343,000 divided by 2, and then multiplied by 0.04 squared. And I'm coming up with 274.4. Units for work? Joules. Okay, any issues on the spring? Good? Pretty good? Mm-hmm.
Would you provide us with the formula for Hooke's law, or do we have to look at that?
You need to know Hooke's law. KX. KX. You can remember KX.
But for a problem like this, you will at least provide us 2 pieces of information.
Yes. For sure. All right, let's drain a tank. Hopefully these are feeling sweet by now. Right? Yeah. So coordinate system right there. Our acronym, which you have all memorized very easily by now, work is equal to? Add volume. That's going to be our acronym, ADD, multiplied by volume. Volume is not the volume of the tank, it's the volume of a slice of water. ADD, acceleration density depth, or acceleration density distance, however you want to think of it. So let's see. So right away we know the first 2 pieces. Acceleration due to gravity, 9.8. Density of water, 1,000. So that part's kind of autopilot. Now let's go over to our shape and be a little more selective. We're going to pick a representative cross-section right there. That's a representative cross-section at a height of y. That representative cross-section is a disk. We know how to find the area of a disk. It all depends on the radius of that disk. There's the radius. And that cross-sectional disk becomes a volume when you multiply it by dy. So we've got a disk, paper thin, it's flat, multiplied by dy, then all of a sudden it becomes a hockey puck. It's got a little thickness. Right, Dustin?
Yeah, I love hockey.
I know. So I threw it out there. I looked at you and I thought, oh wait, we could think of it as a hockey puck.
Now I understand.
Now it makes sense. We've got our disc, add some thickness, we've got our puck, ready to roll.
Hockey,
So let's hockey it. What we need is the radius. The radius is a function. Is it clear that the radius depends on where your height is? Right, that radius changes depending on what the height is. So what we need is this function over here, the edge of that cone. That function is telling us how far away we are from the y-axis.
Y minus 0 equals 8.
So the cool thing is that for a cone like this, it's going right through the origin. So that means that all we need to know is the slope of that line.
Which is y equals 8x.
So y equals 8x. That is the equation right there. The radius is a horizontal distance, though, so
Y over 8.
y over 8. So we're going to isolate x because we want this function to measure horizontal distance, not vertical distance. Now it's measuring horizontal stuff. And the area of the disk is pi times the radius squared. So that y over 8, that is the radius. This is the radius.
Wait, why do we need to switch it from y equals 8x?
So the r value is a horizontal distance. When we have the function written like that, it's measuring vertical distance. But as soon as we isolate x, now it's measuring horizontal. It's telling us how far we are from the vertical axis.
No, from 0.
So that r is horizontal, so that means it's an x distance. It's horizontal distance, so we want to isolate x. So that, oh, I forgot to do the d in here. Let's move this over. So you're crowding out the d. Move over. Move over, area. Now, if we put a dy in here, this is now volume. So this chunk right there, that is the volume. The one piece that we're missing, we've got the A, the first D. What's the second D? The distance that that cross-section of water travels. What distance will it travel?
8 minus y.
8 minus y. So 8 minus y is the second D. Limits of integration? 0 to 8. There are slices of water between 0 and 8. All right, so there's our main setup.
Can I pull up the pi?
You can. You can pull up the pi. Any part of that integrand that you are not seeing clearly? So that volume is not the volume of the cone. It's the volume of the hockey puck. So pulling constants out, we'll have 9,800 times pi divided by 64. Integral 0 to 8. We're going to be left with 8y squared minus y cubed dy. So the only variable pieces that are staying in here, we have the 8 minus y, and we have that y squared. The 8 squared is a constant, so that pops to the front. All right, integrating that, not a problem. We don't need to do it. Any issues on that setup? Is it becoming crystal clear? You're not convincing me.
For like the next step, let's say when we integrate and you did, so you would get 8 over 3 y cubed, but would you be able to take out the 3 and just put like in the very front of the 9,800 times
This
1/3?
3?
Yeah,
No.
that's what I thought.
Yeah, we can't because of the subtraction there.
Okay, that's what I thought.
Right, so we've got that subtraction, so we're going to have that. So we can't pull out any, the only way we can pull a constant out is if it's in both of those terms.
Can we do a trough one?
Yeah? Boy, I'd love to. That sounds great.
That's scary.
Let's do a trough.
No.
Let's do a trough. Why not a trough?
It's the same day every year.
This trough has a bunch of fractions in it. Can we modify it a little bit so we don't have a bunch of fractions? Yeah, 'cause I'm not going to like try to hose you with fractions.
Thank you.
So let's do it. Let's change it up a little bit. So we're going to modify it so it's a little friendlier. Let's do the front of our trough like that. We'll still use the 10 for the depth, or the length backwards. We'll still say it goes back 10. Let's make the base something that's divisible by 2.
2.
So it's not
0.
0. Okay, well, we're going to do 6 and we're going to do 8. All right? Not 0. Then it's no longer, I mean, it's still a trough, I guess, but. Okay, so,
Is our height still 7?
yeah, let's go ahead and still do a height of 7. That's actually, do we want that to be? No, that's good. That shouldn't be too bad. It's odd. Okay. So first thing, when you're thinking about your representative cross-section, that's a rectangle. So when we come across the face of the trough, we are going to build a rectangular cross-section. So if we look up at our picture here, there is our rectangular cross-section. And we know how to find the area of a rectangle, base times length, so that's no problem. Okay. So in order to find the work, we know that we're going to do ADD volume, add volume. And we know that we're going to have the 9.8 times 1,000. So we are going to think of this layer of water, this cross-section of water, it's at a height of y. So what would be the distance traveled by that layer of water?
7 minus y.
7 minus y. So there's the ADD.
It's not.
So there's ADD. So now we have to find the volume. And the volume is the volume of a slice. And that slice has a cross-section that's a rectangle. So we find the area of that rectangle, multiply by dy to make it a little thicker, to make it a slice and not a cross-section. So really all we have to do is find the area of a rectangle. Multiply by dy. So that right in there is going to be area of rectangle. Okay, so the area of a rectangle, width times the length. The length is 10, that's easy. So all we need to do is figure out what W is. That's our whole goal. So now we imagine the coordinate system here, and usually we stick it right in the middle. So there's our coordinate system. And we have a line right here, just like the last problem. We had a line that measures we wanted to measure the distance from the vertical axis over. So we're going to find the equation and solve for x. And then that'll be kind of the radius of the trough. We want the diameter of the trough, though, so we'll multiply by 2. So this line, this point right here, is 3, 0. 6 divided by 2, so that's 3, 0. This one is 4, comma what up here? 4, comma 7. So now we use the point slope formula. So we're going to do y minus 0 equals slope times x minus 3. Slope is 7. Rise over run. Everyone agree? Rise is 7 minus 0. Run is 4 minus 3. Rise over run. So y will be 7x minus 21. Divide both sides by 7. So that is now measuring from here, from the center over. So that is going to measure half the width. Right, when you isolate x, it's measuring from the y-axis over. If we want the full width, what is the full width going to be?
2 times that.
Yeah, just 2 times that. 2 times that's the width. And that drops in right here. So now we have the width of the rectangle multiplied by the length of the rectangle, which is 10. Limits of integration? 0 to 7. So let's see what constants we can pull out. We can certainly pull out the 9800.
2 and 10.
looks like 2 and 10 is a 20, so that'll come out. And then the only thing left in here, we have these two binomials. So we have to FOIL them out. So we'll do 7 times y over 7, which is y plus 21. Doing that and that. And then we do that and that. So that's minus y squared over 7 minus 3y. dy 0 to 7. And then we can integrate and evaluate.
For point slope, we could have used the other coordinate, right?
Mm-hmm.
And it would have been the same.
So you could do easily, you could do y minus 7 is equal to 7 times x minus 4. Doesn't matter which point you use. If there's a point with a 0, it's always easier. Yeah, but you could use the other one. Any other questions up to that point? We can combine the y and the minus 3y to minus 2y, and then we have to integrate, plug in the 0, plug in the 7, put on our units of joules, and then we've got it. All right. So, force. Oh, another trapezoid. You're going to love trapezoids. If you don't already. So this one is force, though. Force has a slightly different acronym. Super close. What do we do for force here? So ADD area. So force is going to be the integral of add area. But it's really similar to what we just did. The only difference is that we have an area instead of a volume. But when we see that area, we have to remember it's not the area of this trapezoid. It is the area of this horizontal element. It's the area of that strip at a height of y. So the area of that strip is W times dy. Right? The width across is W, bless you. The width across is W, and if we multiply by dy, we are now getting the area of that strip at height y. So let's at least do our ADD part first. We're going to have the 9.8. We're going to have the 1,000. What is the distance that that strip is below the surface of the water?
1. 3 minus y.
3 minus y, right? Because the height is 3. Y is measuring that distance. This distance is 3. So the distance in between, the complementary distance, is 3 minus y. Okay, so there's the ADD. And what about limits of integration? 0 to 3. So now we need W. That's the hard part, finding W. So we do what we did in the last problem. Throw in a coordinate system right in the middle. We're going to need to find the equation of this line. This point right here is going to be 1, 0. This point up here is going to be 2, 3. The slope between those 2 points, y minus y over x minus x, the slope is 3. All right, so that means that the equation of this line right there, that line has equation y equals 3 times x. Plus, oh, I didn't finish it off. I need more space. 3 times x, but we have to get our y-intercept in there. So it's going to be y minus 0 equals 3 times x minus 1. Point slope. So the y-intercept will be minus 3. Then we isolate x. So that function is now measuring half that strip length. That function right there is measuring from the y-axis over. When you write it as an x value, it's not measuring horizontal distance, so it's measuring from the center over. How do we get w?
Multiply by 2.
Multiply by 2. Same as it ever was. So there's w. Multiply that by 2. So now, area is the width of the strip multiplied by the thickness of the strip. So this is area, that thing right there. That is area. Not the area of the whole face, it's just the area of a rectangle. All right, steps there, numbers there, letters there you're not sure about? ADD, area.
Where would we use the other formula where it's like ADD volume? What kind of
For
problems?
work.
For work.
So the ADD volume is when we have a volume of tank and we're draining it or pumping it out. ADD area is where we have a face with water pressing against it, or some fluid pressing against it. Some liquid. Yeah.
So when solving for x, is it better to combine terms like that rather than leaving it as like y over 3 plus 1?
No, it doesn't matter.
Okay.
Doesn't matter. I'm going to not do that because I look up here and I know that I've got to multiply these two together. And it's just a little easier to multiply those together if there's no fractions. If the fraction is a constant, then it can come all the way to the front and we can just deal with it later. But if you made it y over 3 plus 1, then you have to distribute and use a fraction, which is fine. You can do it.
Okay, but it's a lot easier.
It's going to be a little easier if we have no fraction inside these two variable pieces. So when we pull out the constants here, we'll have 9,800 multiplied by 2/3. And the integral, the only stuff that's left is the 2 there. So we're going to have minus y squared plus 9. Everyone agree on that foiling? Minus y squared, we're going to have the inner and the outer are going to cancel. And that, of course, we can integrate pretty easily. All right. Comfortable with the volume and area, these things? Working for us? Working for us? Let's go to the hyperbolics. We're only curious about derivatives and integrals. So just make sure you know your basics. Derivatives and integrals. I won't ask you to convert to exponentials. You'll do that in other classes. We don't need to do it here. So we just want the basic derivatives down. So differentiating this. Some of you can just differentiate it fine right off the bat. If you have any trouble, if you look at this and you're not 100% sure, it's going to be a little bit easier if you have any ambiguity to rewrite it like that. Because this is a combination power and chain rule. And it's going to be a lot easier to see the power rule piece of it if you put that exponent on the outside. Do you have to? No, of course not. But if it makes it easier for you, do it. So then here we pull the 4 down. The base stays the same. Right? You never change the exponent and the base simultaneously. Only one of them gets changed at a time. So 4 comes down, we subtract 1, and now we'll pop the 3 right in there. So we have minus 4 sinh cubed of 2x. Now we differentiate the base. There's the base. And so we differentiate the base, that's going to be cosh of 2x. Now we differentiate the angle, that's 2. So we're just drilling in. Start on the outside and move in. So our simplified answer will be -8 sinh cubed times cosh. All good with that one? So power rule combined with chain rule. Okay, derivative. So another thing that's helpful is to think about your trig counterpart, because there's a parallel process happening here. So if you're trying to do it all at once, that's fine if you're totally comfortable, but if you need to, come off to the side and remember that the derivative of cosecant is minus cosecant cotangent. And so that's the model from trig that we're going to use. So the derivative of cosec is going to model that. It's going to be a minus cosec cotangent type of thing. And we may have to think about the minus sign. The rule in our head is that sinh, cosh, and tanh, those are the primary three, they differentiate positively, and the other three differentiate negatively. So we will keep a negative, because this is not one of the primary three. All right, so here we go. So the derivative of a log starts out 1 over the inside. So 1 over cosec 11x. That's 1 over the inside. Anytime we differentiate a log, that's where we start, 1 over the inside. Now we multiply by the derivative of the inside. Okay? So we want the derivative of cosec 11x. And like we just said, it's going to model that. So derivative of cosec, we know there's going to be an 11 also, so if you're comfortable popping it to the front right away, that's good. It's going to be negative. Cosec cotangent. So cosec 11x times cotangent 11x. Common factor of cosec 11x. That's going to go away. We'll cross those two out. Simplified form will be negative 11 cotangent 11x. Not too crazy. These ones you don't want to miss because they're a lot less work, but you just have to do enough work to make sure you know what you're doing.
Natural log.
This was in log form. So log form, so you could write the answer right down. If you don't see it, if you have a fraction and you're going to use u sub, you're going to use u as the denominator. And when you take the derivative, here's how you know that you could have just used log form. When you look up here, if the derivative of the denominator is the numerator, it's in log form. So you could have cut straight to the chase. So if we are going to do it with u sub, we would end up with integral sinh x dx, that's du. So we have du over u. That's natural log of the absolute value of u. When we do our back substitution, once again, we notice that, oh yeah, if it's in log form, you always get natural log, absolute value of the denominator, if it's in log form. So if it's kind of in log form, sometimes you can manipulate it by multiplying by something and put it in log form, modify the coefficients. If that's the case and it's not obvious to you, it's like close to log form, but you're not sure how to make it in log form, just use u sub, and you will get to the same place. Does not matter. All right.
When I had a general question about
Sure.
like noticing that it's log form. I'm like traumatized from my last class where I had to write out like a rationale for every step. Do you want to see like this is in log form? So
No,
okay.
I believe in you. Yeah, I mean, it's totally obvious. I mean, if you're testing at home or something, or, you know, not in front of my face, then maybe I would, but yeah, that's totally fine. I'll know what you're doing. Right.
Thank you.
I don't know if I know what you're doing, but.
You will never know.
Okay,
Am I
so
right minus C?
you can write minus C if you want. I can't believe no one's ever said that. That's very funny. Yes, you can write minus C instead of plus C. That's totally fine.
You'll dodge us points if we forget to put plus C.
Yeah.
Just making sure.
You mean you're not going to put plus C or minus C? Then you'll lose a point. All right, let's take a look at this one. So this is parallel. Let's go over to trig for a minute. And tan squared of x dx. Does anyone know the antiderivative for tan squared?
No.
Secant tangent.
No, for tangent squared, not just tangent. Don't know off the top of my head.
1 over secant squared.
Natural log of
Whoa.
cosine x, something like that.
Not quite.
Not
So
quite.
that's close. So one important thing is that if you look at the 6 trigonometric functions, sine and cosine essentially integrate to each other. There's a minus you have to deal with. But all the other 4 do integrate to log functions. Tangent integrates to log, secant integrates to log, cosecant integrates to log, cotangent integrates to log. But this is a tan squared. So tan squared, we don't have an immediate antiderivative. If it was secant squared, the antiderivative would be tangent, if it was secant squared. But it's not. So when you have something that does, what it should remind you of at least is that it looks very Pythagorean in nature. You've got a tan squared. So what we're going to use is an identity here. And we know that tangent squared is secant squared minus 1. And so that's going to be the trick for this trig one, is that if we replace tangent squared with secant squared minus 1, let's move that identity up there. So this is going to end up being the integral of secant squared minus 1, and this we can do. Right? This is going to be integral of secant squared is tangent minus x plus c. So that's kind of the parallel process that we're going to have over here. So tan squared is going to act like tangent squared. It's not going to have an immediate antiderivative, so we're going to have to use an identity. Now, the one identity that we talked most about, the primary, is cos squared minus sinh squared is equal to 1. So what should we do to both sides if we want to get the comparable identity that relates tanh and sech? What should we divide everything by?
Cos squared.
Cos squared. So we're going to divide everything by cos squared. So divide this by cos squared, divide this by cos squared, divide that by cos squared. So that's always your sort of go-to. If you can't remember an alternate Pythagorean identity, you just divide by what you need to divide by. You remember the basics, sine squared plus cosine squared is 1, or cos squared minus sinh squared is 1. Do your division, and we end up with 1 minus tanh squared is equal to sech squared. So that gives us our way to isolate tanh. So we're going to have 1 minus sech squared will be tam squared. Now we can integrate. So this is going to be, so we'll come down here. So this is going to be the integral of 1 minus sech squared. Integral of 1 is x. All right, so now we have to think about derivatives again. What is the integral of sech squared? Say what?
Kosh, or top?
No, it'd be tangent.
Just tangent. Tangent. Because derivative of tangent is secant squared. Derivative of tangent will be sec squared. Yeah. And so this gives us x minus tangent x plus c. So derivative of tangent is positive sec squared. So if there's a negative, it just floats in front. Is that good?
Remember that one.
All righty. Next, one more integral. So I'm not going to put a definite integral on there, but let's go through the integral for the tangent. How do we integrate tangent or tangent? So we're going to go to its basic reciprocal or whatever that, the quotient form. So this is going to be the integral from 0 to ln 10 of sinh over cosh. And then what form is that integrand? Log form. The derivative of cosh is sinh, so we can immediately write down this. And this is going to go 0 to natural log of 10.
So that's what I was thinking of, is the natural log of cosh right there with the just
Yeah.
tangent.
So if it was just tangent instead of tan squared, yeah, exactly. Yeah, so just like the trig functions that all integrate to logs, the same is true with hyperlogs. Yeah. So we won't. So you could then plug this in and simplify it. Let's just do one more step of simplification. We don't need the absolute values because cosh is the hanging cable, so it's always above. So we're going to have cosh of natural log of 10 minus cosh of 0. And what's cosh of 0? 1. Hanging cable goes through 1. So we could do that. And if we were dealing with exponential forms for the cosh, we could simplify that. We could change to the exponential form and simplify it. But we're not going to do that. Not what we're going to do. Okay, so questions from, we have 5 minutes, so whatever you think. Anyone have a homework question? Or a random question? Jordan?
So would you, plug in the lower and upper integration values into ln or natural log?
Yeah.
Or would you do it, why wouldn't you do it like outside of it?
Say that again.
Like,
So these are x limits, so we're going to put them in for the x. So we're putting these, I know what you mean. I'm sorry. We didn't finish this off, did we? This is natural log of 1. That's what you were talking about, right? Yeah, so we are plugging this to the inside. Cosh of 0 is 1, but then natural log of 1 is 0. Yeah, good point. Yeah, thank you for catching that. So we would simplify it just up to this point for now. Yeah, nice catch. Good. All right, anything from homework that you got snagged on that you want to look at? Do we want to do another type of volume, like a cylinder, or
Force against the wall, but with a
different shape?
with a shape in the other shape. Like
Wait,
a
wait.
window, like a window.
Oh, a shape in a shape?
Yeah. Shape within a shape.
Shape within a shape?
Yeah.
I mean, so the classic one with a shape in a shape is this type.
There we go.
So there we have a shape in a shape. So here we're going to have a diving pool that's 6 meters deep, full of water. We've got a little viewing window. The radius is 1.5. Okay. So we will not get through the whole problem, but let's set it up. Tell me what the equation for this circle is first.
So that's 1.5 radius, right?
So 3/2 is the radius. So what is the equation of this circle? X squared plus what?
Plus y squared.
Nope. Y what?
Y plus 1/2 squared,
Close.
or 1.15.
Close. We have to subtract though, right? If we're shifting up. So it's going to be y minus k. So it's going to be y minus 3/2 quantity squared equals 9/4. So that's going to be the equation for that circle if we put the coordinate system right at the bottom of the pool. When we draw our element is where there's constant pressure. That's horizontal. Horizontal distances are measured with x values. So we need to solve this for x. This function here, or this equation here, needs to be rewritten, and we need to solve for x. So that's going to be, we're going to subtract off that piece, take the square root of both sides. So it's 9/4 minus this squared. And let's call the width of this strip W. W will be equal to what? What are we going to do with this square root? W, double it. Double it. So 2 times the square root. And if you do simplification here, if you square the 3/2, you're going to get a 9/4, but there's going to be a minus. So if we simplify what's in here, we're going to get minus y squared. And the middle term here is minus 3y times minus 3y over 2 times 2, so that's minus 3y. But then there's a minus, so we're going to get plus 3y. If you FOIL that out. You know how to FOIL. Okay, so there is our W. So now we're ready to roll. Our force is the integral limits of integration? 0 to 3. So even though the pool is 6 meters deep, the limits of integration always reflect the physical reality of the region that you are working with. So that is 0 to 3. And then we do our A, D. How deep is that element?
6 meters.
6 minus y. Right, that's the element at y. So 6 minus y. Now we do the area. And by area, we mean area of our little strip. So area of a strip is 2 times the square root of this multiplied by dy. So that is our setup. So look at each of those. We'll stop there. I'll see you on Monday. I can just watch you perform your first masterpiece.
How are you feeling this?
We shall see. The world needs bitch figures too. All right, so have a good weekend. Any questions, you can write them into that OneNote area, and I will get back to you over the weekend. Snowbird. Isn't that place so fun?
It is, yeah, I'm actually going on spring break.
You are?
Yeah.
We went there for spring break 2 years ago when my kid was looking at University of Utah.
Nice.
And it snowed like 2 feet the day we got there. It was so good.
I only been there once. We got this one friend.
We snowboard. We can't go to Ulta.
You're right, they don't like snow.
They don't like snowboarding there.
The distance is 6 minus 1.
So annoying.
The pool height is 6, right?
Right, so if this pool is filled with water, we're going to say that this is the element at a height of y. So that's measuring from the bottom of the pool. And so that whole distance is 6. So that distance in there is 6 minus y. Yeah, good job. No, study it all. You are like remarkably impressive.
That's hard not to.
I have complete faith.
If I average 3 points a question.